Dynamical Systems, celebrating the 80th birthday of Marco Antônio Teixeira. The workshop on dynamical systems is a traditional scientific event in the fields of dynamical systems and ordinary differential equations in Brazil. It has been held annually since its the first edition in 2009, thanks to the vision and initiative of Professor Carlos Gutierrez, Jorge Sotomayor, Djalma Libre, and Marco Antônio Teixeira. At this point, we would like to invite the following professor to join us at the opening table for this ceremony. Professor Ricardo Miranda Martins, Director of the Institute of Mathematics, Statistics and Scientific Computing in MAT. Professor Kétia Baroa de Rezende, represent the Dynamical System Group of IMEC. Professor Cláudio Buzzi, represent the scientific and the organizing committees of the workshop on dynamical systems. And Professor Djalma Libre, founder of the workshop on dynamical systems, along with Professor Teixeira, Sotomayor, and Gutierrez. We now invite the professor to deliver their speech.
Good morning, everyone. Bom dia a todos. Welcome to UMEC. Welcome to Unicamp. It's a pleasure to me to be here at this opening of the 30th edition of the workshop on dynamical systems. As a PhD student, I helped to organize the first edition of this event. And even before that, I remember Professor Marco Antônio talking about his idea for the workshop. His goal was to bring researchers from abroad to present cutting-edge research in dynamical systems, and also to encourage students to give talks. This edition is very special to us because we are celebrating the 80th birthday of Marco Antônio Teixeira, who has dedicated his life to mathematics. The name of the event is MAT80, make us wonder if it's about mathematics or about Marco Antônio Teixeira, showing how dedicated to mathematics Marco is. Being here today as the director of the Institute of Mathematics, Statistics and Scientific Computing of Unicamp, and having been one of Marco's PhD students, fills me with great pride. Marco was also a former director of the Institute, which makes this moment even more special. This year, on Wednesday, Professor Marco Antônio Teixeira will receive the title of Professor Emeritus of Unicamp. The idea for this honor started about 10 years ago, and it's a happy coincidence that it's happened now during this conference, something that only mathematics could offer to us. Finally, I want to thank everyone who helped to organize this event, especially the staff from the section of events of IMEC, also the organizing committees and our local committee who worked so hard in the recent weeks. A special thanks to Douglas, who shared with me all the challenges of organizing this event and the challenge of waiting for the responses from the funding agencies. I also want to thank those agencies for supporting this event. I won't take much more of your time, but I hope you all enjoy this event. I don't know who is next. Catch it, please.
Well, good morning, everyone. I think I speak for all of us gathered at this conference when I say that it is with great joy that we come together to celebrate the 80th birthday of Marco Antônio Teixeira. Some of you will no doubt speak of Marco's profound and lasting contributions to the theory of discontinuous vector fields, reversible systems, as well as the significant influence his work has had on your research, whether directly or indirectly. In mathematics, we often celebrate theorems and breakthroughs. Yes, it is equally vital to celebrate the human connections and the mentors who ensure that the field thrives. Marco embodies this ideal, reminding us that mathematics is not just about solving problems, but about building a community of researchers who interact, support, and uplift one another. And I think we witness to this fact here today. Marco has been a catalyst for progress in mathematics, not just collectively, by investing in emerging mathematical centers throughout Brazil and international cooperation agreements, but also individually. He has been an extraordinary mentor and collaborator whose guidance, encouragement, and generosity have touched the lives of countless colleagues and students, many of whom are here today. Throughout this week, we honor not just a remarkable mathematician, but also a truly inspiring human being. What set Marco apart is not only his exceptional and extensive body of research, but also his unwavering commitment to seeing others succeed. His unique ability to take a genuine interest in others, whether through collaborations, insightful feedback, or encouragement to pursue bold ideas, has left a profound impact on all who have worked with him. This, of course, explains his interest in a remarkably diverse range of research topics. I recall a colleague whose specialty was in PDE, asking Marco a question. Before long, their discussions culminated in a joint article with the answer. So Marco knows no barriers. He talks to anyone. I've had the privilege of witnessing Marco's generosity firsthand, as his office has been next to mine for almost 30 years. He would often stop by to hand me a paper saying, "This might interest you and be relevant for your work," or to inquire about how a certain student was progressing with their doctoral research. Many other times he would propose a problem related to my work and was always ready to discuss and answer questions. His office door was always open. Students and colleagues alike would visit, leading to a lively conversation, whether about mathematics or soccer. Soccer was a favorite. I never took part in these discussions about soccer. I wasn't up to the level. The livelier the conversation, the greater the chance I could overhear it through the thin wall separating our offices. The best was the early morning laughter that brightened the day of his neighboring colleagues. As we honor Marco today, we celebrate a career defined not only by remarkable scientific contributions, but also by an extraordinary legacy of collaboration. A career defined by this rare quality, the ability to inspire and elevate others. Let his story motivate us to emulate his generosity of spirit, fostering an environment where others can thrive. In doing so, we ensure that, like Marco, we leave the field better for those who come after us. Congratulations, Marco.
Good morning. Ladies and gentlemen, esteemed colleagues, dear students and friends. It is with great honor and immense joy that we begin this scientific congress, an event dedicated to celebrating a journey that has been the inspiration of generations of researchers and a contribution to the advancement of science. Today, we celebrate not only the 8 years of life of an exceptional individual, but also the legacy of a scholar whose dedication to research and teaching has transformed many of us. Professor Marco Antonio Teixeira is a true icon in our field. His passion for science and inquiry would know no bounds. Through his competence, rigor, and innovative vision, he not only distinguished himself as a researcher, but also shaped and mentored many of the professionals who today share his ideals of excellence. The impact of his work is, without a doubt, immeasurable. Over these 8 decades, Professor Teixeira has provided invaluable contributions in qualitative theory of dynamical systems, with research that has not only enriched the acknowledgement in our field, but also opened new paths for discoveries. His contribution to the formation of young scientists who were fortunate to be guided by his generosity is immeasurable. As we celebrate this very special milestone in his life today, it is important to reflect on the legacy he leaves, not only his publication, but more importantly, the research group he has founded. The first edition of the workshop has just few participants, and today we can see it became a success. This Congress, which is a small tribute to the hard work and brilliance of Professor Teixeira, is also a celebration of science, collaboration, and a passion for knowledge. Over the next few days, we will have the opportunity to learn from each other, exchange ideas, discuss advances, but also reflect the importance of what he has built and now how we can move forward. Characteristics that have defined and continue to the scientific community. We are honored to congratulate Professor Marco Antonio for his extraordinary achievements and for the example he continues to set for all of us. Professor Teixeira, today we celebrate not only your 80 years, but the life of someone who, with humility and generosity, has positively impacted so many lives. Congratulations, and may this Congress be a tribute to your remarkable career. Thank you very much.
Approximately 25 years ago, and then in 15 years, there was a joint project between Brazil and Spain. And with Marco, we obtained, if I remember well, 3 of these projects. Every project has 3 years of duration, and this project allows that the students of the group of Marco Antonio, Jorge Sotomayor, and Carlos Gutierrez visit our university for some period for doing research, and some people of our group come to Brazil also to do some research. In one of these visits of mine to Campinas, in one of these projects, Marco Antonio said to me that it would be good that we organize a workshop in order that the young people who was at the beginning, the students of Marco Antonio, Jorge Sotomayor, and Carlos Gutierrez, they can go to this workshop, they can see what new results, some of the new results of dynamical systems appears, and also that they have, the students, the opportunity to talk or to present their work in these workshops. And I said, this is a good idea. And he talked also with Jorge Sotomayor, with Carlos Gutierrez, and decided to organize the first workshop on dynamical system, call it the Oficina of the Dynamical Systems in Portuguese. And since this first office works very well, decided to do the second, and so on. And we arrived to the 13th, which is the present one. And in all these workshops, the real father of the workshop was Marco Antonio. He takes care that every workshop continues until the present days. So thank you for this, Marco. And I have the opportunity to participate in all these workshops, and of course Marco also. And perhaps there are no other people who are in the 13th workshop. I don't know. Okay, that's it. Thank you very much, Marco.
We thank the professor for their speech. The ceremony is now concluded. It's my honor to officially declare the opening of the 30th workshop on dynamical systems. Wish you all a productive, inspiring event. Thank you.
Okay, thank you, Anna. Thank you to the members of the opening table. I also would like to extend my welcome to you all. Okay, if you need an assistant, do not hesitate to reach out to me or Ricardo. Please get if you want to. To me or Ricardo or anyone from our local organizing committee. Okay, you meet them. So before we proceed to our first plenary talk, I would like to share a few important announcements. The first one, our official dinner, that's an important one, right? Will be on Wednesday at a barbecue restaurant with all-inclusive food and drinks, okay? You should have received an email with a Google form to indicate your attendance, okay? To pay for the dinner, you can use a QR code which is in the registration desk outside the auditorium. Or if you want to pay by cash, you can just reach out to me or Ricardo too. Okay. The second announcement is that we have reserved 2 Easted rooms, okay, for meetings, online meetings, discussion, working, whatever you want to do. You find them just upstairs, okay, clearly identified with a workshop poster. It's there. Additionally, we have distributed also some blackboards and desks outside the auditorium that you can use as well. And lastly, I'm excited to announce that we will be publishing a special proceedings of this workshop in honor of Marco Antonio Teixeira. It will appear in Matemática Contemporânea journal, published by the Brazilian Mathematical Society, which is starting next year, will be published by Springer. Okay, so that's a nice. I hope you all enjoy the workshop. And now it's my pleasure to introduce our first plenary speaker. Okay, my colleague and senior member of the Dynamical System Group, Kat Abaro de Rezende. She will be talking about the algebra behind the dynamics of isolated invariant sets. Please join me in a warm round of applause to our speaker.
Good morning again. So today we'll speak about the okay. Thank you. So we'll be speaking about the algebra behind the dynamics of isolated invariant sets. Okay, the title seems rather complicated, but it has a story, and all stories are nice to hear. Who are the protagonists? Where did it start? In mathematics, that's sort of hard to say. But let's say we have to start somewhere, and I'd like to start with Poincaré. We won't get into, of course, all of the vast amount of his work, but to me, what is interesting for this talk is he is well known as the father of homology and homotopy, and of course his very famous equation where the Euler characteristic is actually, here we have a small error already, is the alternating sums of the Betti numbers. The alternating is missing there, but anyways. And of course he built this on the very famous Euler formula, vertices minus edges plus faces. And of course Hopf is another giant in the field, also has a very interesting equation for the Euler characteristic where he just counts the index of zeros of a vector field on a differentiable manifold. And Morse. Of course, Morse has his very famous inequalities, and his equality, top Morse inequality, is an equality where he describes the Euler characteristic as the alternating sum of non-degenerate critical points of Morse index. So there are different approaches to the Euler characteristic, but all related to dynamics, to topology, and algebra. So I'd like to start maybe with Morse, saying that Morse's insight was to look at the topology of manifolds via the study of differentiable functions. And so he defined, and let's get a very easy calculus example, two-dimensional, non-degenerate critical points, for instance, of a real valued function, G, he would look at the gradient and look at critical points. And then he would consider the Hessian and would say that if the Hessian was non-singular, then that critical point would be non-degenerate. And he would define his Morse index as the number of negative eigenvalues that appear. So he was interested in looking at how the level sets, inverse images of regular values, they change as you change the values in R, as you pass through a critical value. So that was one of his many interests, and the one that we're interested in speaking about today. So he also was the creator of the notion of handles, that a manifold can be built out of handles containing this unique non-degenerate critical point. So you can start with, let's see if I get this. Here. We can start with the disk and then add another handle and so forth. So, and continue adding handles which have exactly one critical point. So we start with this, and then we add another handle with another critical point, and so on, until we get the full torus. So that was his idea, and he would look at the level sets and see how they change. We have circles, a figure 8, then 2 circles, another figure 8, and more circles till we get to the North Pole. And that's a way to study manifolds through differentiable functions. He, of course, would then look at the gradient of this function, which takes after his name, Morse functions, which contain only non-degenerate critical points. And as he moves along, he noticed, and this is one of the lemmas that I want to concentrate on today, because what we'll speak about today has to do exactly with this lemma. So you start at a lower level, which I'm representing by Y, and we add a handle, and then we have a new level. So the red and the green are regular levels, and of course this red together with this unstable manifold forms a critical level. So he wants to see how this changes, but what he does notice, and this is his main deformation lemma, is that if f has only one non-degenerate critical point of index lambda, that is f of p is between two regular values a and b, where f inverse of b is x and inverse of y of a is y, then the resulting manifold x is actually homeomorphic to y, the bottom manifold, together with the handle. The handle is this d lambda cross dn minus lambda, in this case just d1 cross d1. And it's homotopic, of the same homotopy type, as the disk together with the unstable manifold d lambda, the local unstable. So this is a very important lemma. So what Morse was saying is that you actually change to interesting levels as you add handles to your manifold. And Conley, a few years after, he had this idea. Look, what did Morse consider in his research? He was looking at actually where the flow was exiting. So notice that this is the exit set. And what he discovered is that the Morse index was actually described by the dimension of this unstable set, which is 1. So he really didn't need to consider as much of the topology of x and y as to actually the unstable manifold that joined them in this deformation lemma. So what Conley did was say, okay, so let me look at other dimensional handles. Of course, Morse did this in any dimension. So Morse studied, Conley studied, and actually, to his credit, he called this the generalized or the Morse index. He never called it the Conley index. We, in tribute to him, refer to it as the Conley index. But he noticed, look at what Morse is doing. He's isolating in a handle one invariant set, which happens to be a non-degenerate critical point. And the y is exactly the green areas, the exit sets. And he said, well, what is really important in what Morse was doing was the unstable manifold. So how about if we collapse to a point the stable one? So if we deform, as Morse did in his deformation lemma, we deform along the stable manifold, look at what we get. When we deform an attractor along the stable manifold, we can get to the square, eventually to a point, because it's all homotopically equivalent. And then, since there is no exit set, the empty set is identified to this point. So what we have is a sphere of dimension 0. If we deform this along the stable manifold, what do we get? Well, we get a square, and now if we continue to deform along the stable manifold, we get a piece of a one-dimensional disk. And when we identify the two exit sets of this disk, we get a sphere S1. And similarly, we can do this by deforming along the stable, getting a square, and when we identify the boundary of this square to a point, we get a sphere S2, sigma 2. So notice that what Conley is established here is that the Morse index is actually the dimension of these spheres. And this is what is now known as the Conley index. The Conley index isn't a number. What it is, it's a type of space, the homotopy type of a space. So that's the difference, but it does connect to the Morse index. But what's amazing about this index is that what Conley noticed is, why is it that we have to consider non-degenerate critical points to isolate? Why can't we just consider arbitrary invariant sets that can be isolated? Why do we have to restrict to this analytical condition when it really is a topological problem? So he went on to define, let n be a subset of X. The maximal invariant set of n is defined by all the points X and X such that the flow is in n for all time R. So that will be the maximal invariant set that you have in n. So for instance, if we consider this annulus, this gray annulus, what is the maximal invariant set in that annulus? It's this periodic orbit. Why? Because it's inside the annulus for all time, backward and forward. So it is the maximal invariant set. If I consider my neighborhood n to be the southern hemisphere here, what is the maximal invariant set? What are the orbits that are inside the interior of n for all time, backward and forward? Well, certainly the periodic orbit will be here, but also all the orbits that are here below the periodic orbit. So that's an isolated invariant set for this choice of n. So we can actually consider sets that are way different from a non-degenerate critical point by considering this topological definition. In this case, n is said to be an isolating neighborhood for this maximal invariant set S in X. Okay? Next, there are sets that cannot be isolated. So for instance, if we take the center and we look at the origin and we say, okay, let's try and isolate this. So is there a neighborhood that contains that origin and for which the center is the maximal invariant set? And as we can easily see, that's not the case, because no matter how small the neighborhood that I choose around the center, it will never isolate the center. There will always be a periodic orbit in there. So that's, let's say, an example of an invariant set for which the Conley index cannot be defined. His index will only be defined for isolated invariant sets. So how does he proceed to define this? Well, he remembers what Morse did. Morse had one level X, then another level Y, and their connection. So he needs to define a pair, which he will do, as Morse did, XY. He's going to call it NL, but it's the same idea. Okay, so he'll take a pair, NL, of compact sets in X, and he's going to call it an index pair. Why an index pair? Because it will help him compute the index. So it's a pair of spaces where L is contained in N, and N minus L, if we consider the closure, is an isolating neighborhood for S and X. So, and with certain properties, L has to be positively invariant, which means that once we are inside L, we can't go back into N minus L. The exit set has to be positively invariant. And then the exit set, if the flow leaves our invariant set, it has to leave through the exit set. The exit set is the door for the flow to leave. So it can't leave, let's say, through a window somewhere. It has to leave through the door. So that's what this is saying. Okay. So the Conley homotopy index we have this isolated invariant set, and now we can define the index with the help of this index pair. We're going to say that the index of the maximal isolated invariant set is the homotopy type of the point in space, exactly as we saw with those cubes. We collapse the exit set to a point, and that is what we will call the Conley index. That index is denoted by HS. It's a pointed space, and it's the homotopy type of that space. For instance, let's take a monkey saddle. See, Morse couldn't deal with monkey saddles because a monkey saddle is a degenerate critical point. And so what happens here is you have an isolated, a maximal isolated invariant set. Here's the neighborhood N, and what's in green is the exit set. But that is the same neighborhood if I consider two saddles with a saddle connection, as well as two non-degenerate saddles with no connection. So in all these cases, we have exactly the same index pair, therefore the same index. So in a sense, the Conley index is blind to what's inside. It's really looking at the neighborhood, what's happening in the neighborhood. But it does bring to mind that maybe one can almost think of deforming the flow when this orbit and this orbit meet, maybe in a transversal intersection, and then these two collapse, the index is maintained. So that actually, we won't speak about that today directly, but that actually is a very important property. When you have a one-parameter family of flows and you have a neighborhood, and in it, as the parameter changes, bifurcates or whatever, the Conley index is maintained. So one can study continuations via the Conley index. So, of course, for this theory to take off, you need two foundational results. One is that these index pairs exist, because if they don't exist, we go nowhere, right? But they do exist. It's a difficult and long proof that Conley provided us with. And then the invariance of the index pairs, which means that if I have two index pairs for my maximal isolated invariant set, then the Conley index is invariant. The two Conley indices are homotopically equivalent. Okay, so now, of course, once we have a space, the homotopy type of a space, the natural thing to do is compute its homology. And so we have the Conley homological index. That will be a group, which, of course, one would like to look at its rank. So in order to get a number, so we can have the group itself, and here are some examples. For instance, now I can compute the Conley index of a saddle periodic orbit in dimension 3. So when I compute this and this is a round handle where the exit set are these two annuli, and when I collapse the exit set to a point and deform the isolating neighborhood along the stable manifold, what we get is this sphere, which now we connect these 2 points to get a wedge of a sphere, one-dimensional sphere with a two-dimensional sphere. The same thing here. We've just seen this. And what do we get when we look at the Conley index and collapse the exit set? We get the wedge of two spheres. So this is the procedure to get the homotopy type of a space. Now we want to compute the homology of the space, and later on, probably the rank of that homology group to get a number. So we eventually want to work with some numbers again. So this is just the notation of what I just said. This is the Conley index, this is the homology, and this is the numerical Conley index, which is nothing but the dimension of the homology Conley index if we're working with the field. We get the dimension. So here, just with the previous two examples that we just talked about, we can compute the homology of S1 wedge S1, here it is, and we can compute the rank. It's 0 in dimension 2, it's 2 in dimension 1, and 0 in dimension 0. The same thing here for the torus, the periodic orbit. We have the space, the homology, which will be 1 in dimension 1, and it's also z when I is 2 in dimension 2. So when we write out these numbers, we can write them out in a vector form. Okay, so where's the algebra that we can, let's say, follow with these sets? I gave you a hint about the continuation, about the deformation of the flow. Well, Conley had this idea, this local idea, that these sets, these maximal isolated invariant sets, can be very rich. They can actually be components of a chain recurrent set. For instance, a periodic orbit would be a component of a chain recurrent set, but it actually can be much richer. For instance, just to mention, if we have a Smale horseshoe, and here we have some specialists in the audience, and then we consider its suspension in a solid torus. That is an example of a component of a chain recurrent set, which would be, we would represent in our representation as one of these points, as one of these MJs. So these sets can be very rich with complicated dynamics. But the theorem, his theory holds in those cases also. So Conley's fundamental theorem is that given a continuous flow, he doesn't need differentiability at all. And so given a continuous flow with a chain recurrent set, there exists a continuous function called a Lyapunov function, which has the property that if you're not in this chain recurrent set, the flow lines, the function decreases along the flow lines, which is this first condition. And if you are on a component, it's constant. Okay, so that's the idea. And Conley moved on. You don't only have to consider the components of a chain recurrent set. You can actually unite them into a maximal isolated invariant set and consider his theory for this also. So you can unite, for instance, two sinks and a saddle, and this will be your new set. The theory holds in the same fashion. The only provision that has to be taken care of is that you're flowing from the highest index set to the lower index set. So that's, you have to have this connection from a higher index set to a lower one. And that taken care of, this theory will still hold. Okay, so he defined an index filtration. So this reminds us of what Morse did with his level set approach with regular values. So with this index filtration, he gets this nested filtration of compact sets with the property that if I look at any two consecutive ones, I have an index pair. Therefore, one can always compute the index globally. Now, a next step for Conley was to look at the global connections. So of course, we know that these two are not topologically equivalent, but yet we can still compute, and they will have exactly the same global index as well as local, yet the connecting orbits will distinguish them as non-equivalent flows. So here we have two major mathematicians, Smale and Franks, who looked into these global connections. And they had the following paradigm, which was to, let's look at the dynamics of the basic blocks. What does it mean to look at the dynamics of those MJs, of those sets? It means to look at their connections. And then they would always consider a chain complex description of that dynamics. And every time we have a chain complex, the natural thing to do is to compute its homology. So that's exactly what these mathematicians, Salomon, Fleur, and Witten did. They considered the dynamics of the moduli spaces, the unstable and stable manifolds, through differential topology, created a filtered chain complex. Through algebraic topology, they looked at its spectral sequence. So in some sense, this is what we want to do in a more general setting for surfaces, so we can follow. So Smale's very foundational paper on the Poincaré conjecture in higher dimensions, he spoke about cancellation of critical points. He needed this idea of consecutive critical points being canceled. So, for instance, there was this deformation, and then these two critical points would cancel. So, what do we need to do in order to, let me just check on my time. 15? Oh, great. So, what we need to do in order to understand a little bit of this idea of Smale's is to define this intersection number. And the intersection number depends strongly on differentiability. So the manifold has an orientation which is induced on the flow lines. I won't get into how exactly this is done, but if we look at the major flow lines, the unstable manifolds, they all can be associated with 1 or minus 1, depending on whether they agree with the orientation of the manifold or not. Okay? Then, once we have these, we are in a condition to define what a Morse chain complex is. Remember, I have the dynamics, and now I want to define a chain complex, and later the homology. So this is exactly what Fleur did with his theory, and many other mathematicians followed. The idea is to define this group that is generated by the set of critical points and graded by the Morse indices. So Ck of f is all the critical points of index k. And so you define these groups and then a boundary operator. The boundary operator will look to the connections of these index k critical points with the index k minus 1 critical points. Okay, so then we have the boundary operator. We define this boundary operator with the intersection numbers. We literally just fix the x in here and look at all of its connections to lower index y in Ck minus 1. And when we sum up all these intersection numbers, we get, this is the definition of this boundary operator. And of course, this extends to all chains by linearity. So let's take a quick example. If I have this flow on the sphere, and I look at the connection x to y, I sum up these numbers, it's 0. So x to y produces this 0. I look at the connection y to z, y to z is a -1. Y to z prime is a +1. So I just record that, and this is my boundary operator. It's a matrix. We can do this, of course, for more complex flows. Here still on the sphere with more critical points, and we can just count and register the intersection numbers on this matrix. This matrix has the property that its square is 0. Okay, so now I'll go by this very quickly. The idea is, okay, we can have a chain complex and compute its homology. What if I compute the homology of the homology? And then I register that information in the second page. And then I decide to compute that homology, and I register it on the third page, and so forth. So what we have is a sequence, that's why it's called a spectral sequence, of these chain complexes. This will be the index of the critical point, P plus Q, and R will just be the page number. So we have a differential in the same way. Notice that my domain is P plus Q, and my counter domain is P plus Q minus 1. When I add these two up, it's P plus Q minus 1. So it's a degree minus 1 map. And it also has the property that its square is 0. These are formulas given by Spaniard, which are formulas that are well known to us for homology, the kernel over the image. And here are the pages. And notice that we're always going from an index 3 to an index 2, an index 3 to an index 2. An index 3 to an index 2, an index 3 to an index 2. But the differentials are getting longer and longer. So this is pure algebra, and we're asking ourselves, what does this have to do with dynamics? I mean, this is a complex algebraic machine to compute the homology of the homology in a sequence of these modules, chain complexes. So they're actually, when we study the formulas, they're looking at P plus Q connections, and I want to throw out all the short connections. And this is what this denominator is doing. It's throwing out short connections because I'm at the rth page and I want to look at connections that are long. So long connections. And that's what this sequence does. Eventually, the only thing that will be left is this guy who connects with this one. So notice that this is a long connection. I've thrown out all the others under these formulas. Okay, so we can simplify this by getting a finest filtration, so we don't have many in each level of the filtration. And here I want to describe one of the main results that Cornea, Lima, Mello, and Silveda have had. It's a global two-dimensional version of Smale's cancellation theorem. So what Smale did was a local cancellation, and what we're proposing here is a global cancellation. So we have this Morse chain complex, and what our theorem does is it will look at the algebraic cancellations occurring in the spectral sequence, and they will determine the dynamical cancellations. So it does have a dynamical mean. And then the continuation, which will happen from the initial flow to a minimal flow. And here we're just describing results in dimension 2. So here are my colleagues, Silveda, Cornea, Lima, Mello, Franzosa, and Bertoni. So here in a sequence of just pictures, we have, here is our flow, and I compute its spectral sequence. And then I notice that these two are isomorphisms. In that matrix, they're represented by ones. So in the next, when I look at the kernel over the image, these two are going to zero out. So I look at the green one, which connects H210 to H19, the blue one, which connects this H14 to H13, and what happens at the next stage? They're gone. The algebra cancels and the dynamics cancels. So there's a correspondence between what's happening with the algebra and what's happening with the dynamics. I further continue computing the spectral sequence. I find new isomorphisms, longer orbits, because we're further along the pages. And now, when we look at that, well, what happens in the next step? They also cancel. The algebra cancels and the dynamics cancels. So it's as if the spectral sequence is giving us information on the cancellation of periodic orbits. And this has been done in a variety of contexts. We have dealt with circle-valued Morse functions, even Morse-Bott functions, Morse-Smale with periodic orbits. We have introduced a new notion of cancellation of periodic orbits, which is very interesting, and so forth. And final thoughts, homotopy theory can provide a rigorous proof to the existence of black holes, wormhole deformations, and explain the topological origin. Of course, this is just science fiction. It's nothing concrete, but physicists are becoming very interested in these homotopical deformations. And there is actually this paper, which I always find interesting, and it's a new application of homotopy theory. Of course, here in these applications, we go through singularities. And in our previous case, we were just with in a smooth setting. But this theory has also been done for Gutierrez Sotomayor flows. And here I'll take 2 minutes just to pass the picture. So there it's a picture session. We have now the singular points. The same thing holds. We can compute Conley index because it's for continuous flows. We can build up the manifold through the isolating neighborhoods and blocks. We can realize global connections for singular flows. We certainly have non-topologically equivalent things, and we have homotopical cancellation, that we will move from a Morsification to be able to determine signs, because we don't have differentiability anymore. We define again, the boundary operator of the chain complex, and we compute its homology. And by computing its spectral sequence, which we do, we find the isomorphisms. It's exactly the same thing. And then we have our homotopical cancellation. So it's actually very interesting that it also holds in the singular set. And celebrating this 80th birthday, I have to celebrate all of these mathematicians. Marco, your companions, who have contributed to, all of them have contributed to our work. Thank you.
Thank you. Thank you, Kat, for this amazing talk. Questions, comments? Anyone? Here, Lucas, just a minute. Media.
Katie, thank you very much for this beautiful talk. I was just curious. I didn't, well, my question is about the operator delta, that this is a linear operator, yes? And then the next slide is a matrix. And I was wondering, what's the relationship? So what is this, when you say, sorry, I'm just trying to understand my question myself. So when you extend the operator by linearity, you define the the operator defined on the generators and then by linearity. And then you present the matrices, and that's what I was wondering about the blocks that appear in those matrices. I'd like to understand these relationships.
The blocks. Very quick. The blocks are actually they represent the operators from consecutive indices. So if you look at one, you look at all its connections. So the matrix is the global boundary operator of the chain complex. Chain complex is defined on the whole manifold. It's generated by the critical points, and it has a boundary operator which is this upper triangular matrix with square 0. And so we represent it at the boundary operator in this matrix.
So it's actually a matrix representation of this
Of the boundary operator, global. Okay.
Thank you very
You're
much.
welcome.
Thank you.
I'll be happy to answer questions outside. I don't want to.
No. We are.
We're in time.
Yes. Another question? No? I have a question. I've heard that you've been working with the series in the context of Filipov vector fields.
Yes.
Is that correct?
That's correct. Actually, with one of your brilliant students.
Okay.
We have, and I think she has a poster out there. So this is one more of Marco's incentives. Yes, to think outside the box. So we are certainly thinking outside the box with the Filipov systems, and I think there's a lot that we can do defining the index. It's different though from this context. Notice that what I presented to you, we have continuous flows. Even in the singular case, it's continuous flows. Once we go to the Filipov setting, we have discontinuous flows, and that is harder to deal with, but it's being dealt with. And to define an index, and the next step, once we define the index, the next step is to see global connections. First, we study locally what's happening around the singular points, and then what happens in a global context. For instance, if you have one of these flows where your singularities can be, and your discontinuous region can be level sets, for instance. Actually, Marco Antonio and I and Casagrande wrote a paper way back in 2008 on this, where the level sets were the discontinuous regions, where the flow changed, and they were closed. In that case, they were closed curves in the two-dimensional setting. And that's a global approach. So we always move from something local to understanding the global dynamics. That's what this spectral sequence approach affords us. A possibility to look into those deformations and continuations in general. Okay?
Okay, thank you. Any other question? So let's thank the speaker again. Okay, so before we proceed to our another talk, I have an information, but it's an information about some car with lights on, and it's a Corsa Sedan, so I'm going to speak in Portuguese. Corsa Sedan, placa DED 0074. O farol ligado. Okay. We are on time. If anyone wants to go to the bathroom, I'm just waiting for Marco Antonio. Okay. Just give some minutes. Jaume Gibris, professor catedrático and one of the leaders of the Dynamical System Group from Universidad Autónoma de Barcelona. He's going to talk about the Hopf bifurcation of limit cycles surround a node. Please join me in a warm round of applause for our speaker.
Thank you. Before we talk about mathematics, I want to say something. My first contact with Brazilian mathematics was through Professor Jorge Sotomayor. Soto introduced me. I started to work with Jorge in 1986. And Soto introduced me to Marco Antonio Teixeira in 1996. My first paper with Marco Antonio is from 1997, and my last paper was in 2023. During this period, we have published together 40 papers, some of them with other co-authors. But the more important thing between Marco Antonio and I was that we promote the relation between many Brazilian mathematics and Spanish ones. The participants of this meeting is a proof of this fact. Thank you, Marco Antonio, for all good work on mathematics during many years. Okay, now I start with the talk. We are familiar with the Hopf bifurcation mainly when a focus changes the stability. And with this change in stability and some additional properties, some limit cycles can bifurcate from the equilibrium point. For instance, not sufficiently close to mu0, the equilibrium point is stable when mu is negative and also for 0. And then, if mu change, and the stability with this parameter of the focal change, this produces at least one periodic orbit bifurcating from the equilibrium. The Hopf bifurcation, in fact, in many books is known like the Poincaré-Andronov-Hopf bifurcation, because this the classical Hopf bifurcation is a local bifurcation in which a hyperbolic focus of a differential system lost stability when a pair of complex eigenvalues change cross the imaginary axis. No? Then, under good reasonable assumptions, bifurcates a limit cycle from this. The Hopf bifurcation can take place in any dimension, and when we are in higher dimension than 2, it appears in a central manifold of dimension 2. But in this talk, I will concentrate in the plane. And the classical Hopf bifurcation is from a focus like this. We have a focus at the origin and higher order terms. And then, according these higher order terms, if this focus changes the stability when mu crosses 0, it appears the periodic orbits bifurcating from the equilibrium point. The theorem for the Hopf can be stated in this way. We will see after the difference of this theorem for the focus when we put a node. The first assumption is that the origin of coordinates is a hyperbolic focus for any value in a neighborhood of mu0. But when in a neighborhood except for mu0. These eigenvalues are both imaginary when mu is 0, and then we have a weak focus at the origin. When the weak focus is stable, I present in the stable case. In the unstable is similar. Usually this condition is appears through some Lyapunov constant non-zero, because if the weak focus has a Lyapunov constant non-zero, if it is positive, is unstable, the weak focus. If it is negative, is stable. But here I don't use Lyapunov constants. I only use that the weak focus, by assumption, is stable. The reason of this is that in the node we cannot have Lyapunov constants, because the Lyapunov constants are the coefficients of the Poincare map surrounding the focus. But in a node, the orbits goes to the equilibrium, and since they don't rotate, we don't have the Poincare map defined. So this is a main difference between focus and node. Under these two assumptions, at least one stable limit cycle bifurcates from the origin of this system, system 1, when mu increases from 0. That is, the limit cycle that does not exist in mu negative, but when mu passes to positive, the change of stability creates at least one stable limit cycle. Perhaps can create more than one, not at least one. And if you change asymptotically stable here for asymptotically unstable, the limit cycle which bifurcates is then unstable. And this is the difference between the supercritical and the subcritical Hopf bifurcation. Okay. Now, take for instance this system. The system has an star node at the origin in higher order terms. And of course, when mu is not 0, the node is a hyperbolic. And the first difference with focus, when mu is 0, the origin can be a node or a focus, as we will see later on. In the case of focus, when mu 0 always is a focus, a weak focus. But here, no, here can be, when mu different from 0, you always have a focus, but when mu 0, we have these two possibilities. And of course, what are the conditions of higher order terms in order that it bifurcates some orbits from the origin, from the node? In this talk, I will talk about star nodes, but what I am saying by star nodes also works for generic nodes when these two are different, but at mu 0, they become 0. The same results works. Or for a non-diagonalizable node, like this. No? This is a node that the matrix at the origin is not there, is not diagonalizable. The result that I will talk works for any of these three nodes: the star, the generic, or the non-diagonalizable. But in the talk, for simplification, I only talk with the star node. Okay, so what is the theorem for the star node? We have this system, the star node at the origin, higher order terms. And the first assumption is identical to the focus, but changing the focus for the node. When mu is different from 0, we have an hyperbolic node. And when mu is 0, we only say that the origin is locally asymptotically stable. The theorem can be explained if it is unstable, but I stable, a stable case. So these two assumptions are the same, philosophically the same, changing node for focus. But this third is completely different, because if you have a system with a focus, it's easy to prove that there is a neighborhood of the focus where the focus is the unique equilibrium of the system. But this is not the case for the node. For the node, you need to impose this condition. You can have a node and having in any neighborhood some other equilibrium. So we need to say this. For mu sufficiently small, there is a neighborhood U of the origin containing only one equilibrium point, the origin. This is necessary. Without this assumption, we have counterexamples to the bifurcation of periodic orbits. With these three assumptions, at least a stable limit cycle bifurcates from the origin of that system when mu increases from zero. So there are two differences from focus. This is one, and the other is when mu is zero, the origin can be focus or not, as we will see. Okay, what is the tool for proving the theorem? The tool for proving the theorem is the Poincaré-Bendixson theorem. Is the Poincaré-Bendixson theorem. Recall what say the Poincaré-Bendixson theorem. The Poincaré-Bendixson theorem characterizes how can be the omega limit sets of an orbit or the alpha limit sets. I don't recall the definition. Roughly speaking, the omega limit set is where an orbit dies, and an alpha limit set is where the orbit star born. Alpha is the first letter of the Greek alphabet, and omega is the last letter of the Greek alphabet. Born and died. And the Poincaré-Bendixson theorem is a long to state, but you know what he said. He said that if you take, under good conditions, an orbit of a planar system, of a planar differential system, the omega limit set, where the orbits die, only can be three objects, or a unique equilibrium point, or a periodic orbit, or a graphic. And a graphic, as you know, is a set formed by equilibrium points and orbits which connect these equilibrium points. And there are infinitely many different graphics. But these three objects are the objects where the orbits die under good conditions, or the same where the orbits born. Also one of these three objects. Okay. Now, this is the statement of the theorem, and now I do a proof of the theorem. Since we have the node when mu is zero, the node is stable. So there is a neighborhood of it, probably very small, but where the orbits enter, because this is stable. It's statically stable. So there is a neighborhood, delta, where the orbits enter. But what is for mu zero? When mu is positive but very, very small, now is unstable, the node. So the node now is unstable. What say Poincaré-Bendixson theorem? if you take this orbit, what is the omega limit? The omega limit cannot be this point. And there are no other equilibria here. So it cannot be graphics, because graphics means equilibrium. Only can be a periodic orbit. So this orbit do something and tends to a periodic orbit which is here. What do this orbit? The omega limit. It can be this orbit, or perhaps it can be another periodic orbit here. Not necessarily the same. But why these periodic orbits are limit cycles? If they are not limit cycles, it's because some orbit, there are an anomalous field of periodic orbits. But this is not possible, because we are in an analytic system. And why this is not possible? Because if you take, suppose that this orbit is the first orbit, then this orbit is the omega limit, the first one. If you take here as a transversal section, the Poincaré map, since the system is analytic, the Poincaré map is analytic. But here, in this segment, is the identity, because all the orbits are periodic. And an analytic map of one variable, if it is identity here, is identity in a neighborhood. So here, there is another periodic orbit, contradiction that was the first. So, there is at least one periodic orbit here, one limit cycle, because the orbit must be isolated. Perhaps there are several, but at least one. And this is the proof. This is the proof of the theorem. It is what is written here. I explained that. Okay. So the theorem is proven. Now, now I said that when mu is 0, you can have focus or nodes. And one example of the focus is this. Take this system at the beginning. This system, if this, under these assumptions, is a stable focus, a linear stable focus, a linear stable focus. Then do this change of variables, pass from the time t to the time s, and this system becomes this new system. But dynamically, this system and this has exactly the same phase portrait, because this only is 0 at the origin. And at the origin I have, here I have this focus. And the orbits here and here are the same, but they are only traveled in different time. But the phase portrait is the same, it's a focus, a global focus in the plane. Now, at here, this mu. This has degree 3, this has degree 1. And this system is in the assumptions of the theorem that I proved. So, when mu is 0, you have a focus, in this case. And this system, when mu crosses 0, forms one limit cycle. And now, the example that when mu is 0, you can have a node. Take, for instance, this node. This is a linear node. Do the same. Do this change of time. You get this system. This system and this have the same phase portrait. The orbits only are traveled in different time. And you add this thing here, this has degree 3, this has degree 1, and now when mu, this is in the assumptions of the theorem that I proved, so one limit cycle at least bifurcates from here, when mu crosses 0, but when mu is 0, you have a node. And so the two two cases are possible. Now, another thing. Denote by Fn the maximum number of small limit cycles bifurcating from a focus of a polynomial differential system of degree n. The maximum number of limit cycles that if you have a focus in a polynomial system of degree n can bifurcate the node by Fn. And do the same for a node. And denotes the maximum number of small limit cycles bifurcating from a node of a polynomial differential system of degree n. Then it is known the following lower bounds for the maximum number of limit cycles which can bifurcate. In degree 2, it can bifurcate 3, it's the bounding theorem. In degree 3, it can bifurcate 12 limit cycles from one equilibrium, etc. In degree 7, it can bifurcate 61. These are the best numbers until now. Perhaps the real number can be larger than this, but there are examples with these numbers. And for polynomial system of degree 10, 11, 12, 30, the upper bound is this. For 10, you put 10 here, no? And you get the upper bound. And when n is larger than 30, for the moment, there is examples when n is even, that this is an upper bound, and when n is odd, and larger than 30, there are examples with this number of limit cycles bifurcating from a node of degree n. These bounds for the maximum number of limit cycles bifurcating from a node were obtained for many people. Some of them are here. But all of them in collaboration with Torregrossa. So all the results, Torregrossa plays a role until here, until 30. These results for n larger than 30 are due to Rabanal and myself. Okay. What we can say about the number of limit cycles bifurcating from a node? We have this theorem. If this is the maximum number of limit cycles bifurcating from focus in polynomial systems of degree n. If you add +1 here, then the maximum number of limit cycles bifurcating from a node of degree n plus 2 is larger or equal than this number. And the proof is very easy. The proof is this. Take a system, x point equal p, e point equal q, p and q, the maximum degree is n, having a focus or at the origin with Fn small limit cycles, which realize the maximum number of limit cycles in degree n. Then, and we can assume without loss of generality that the origin, which is a focus of this, the region of this system, which is a focus, is stable. If not, I change the type of sign. So, this is the system, no? Realizing the maximum number Fn. Then, I do the same than before. I change the type from E to S. Then, this system becomes this system here. The system now has increased in degree 2. This system has degree n, this system has degree n plus 2. And they have the same phase portrait because this only affects to the origin. And if this system has this number this number of limit cycles, which have bifurcated from the focus, this system also has this number of limit cycles. Then add, here, add these terms here, mu x and mu y. This system satisfies the theorem that I have proven. So, when mu crosses 0, one more limit cycle appears. So this system has Fn plus 1. But this system has an additional node. So this system, which has degree n plus 2, is an example that has this number of limit cycles in a node. So the maximum number of limit cycles for polynomial system of n plus 2 at least is this. This is the proof of the theorem. And that's all that I want to tell. Thank you very much.
Okay, thank you very much, Jaume. Questions? Lucas.
Just in your example, when lambda is 0, you have a focus also.
Yes.
Yeah, but I was thinking that you are searching for an example that when lambda is 0, you have a node.
This is another possibility.
Yes, because in fact you have a focus and you perturb.
But I have only the focus and mu 0.
Yes,
When mu is not 0, I have a
At
node.
the beginning you explained that when mu is 0, you have either focus or node. And at least I was explaining that you show an example of a node, a real node, and when you perturb the real node, you have the number. Do you know if such example is possible? What do you think?
Yes. This is a good question. I don't have at this moment such an example.
Okay, thank you.
Any other question? Comments?
I have a question. So, Professor, you have proven that at least one limit cycle bifurcates in this situation, in this scenario.
Yes.
Is there any perceivable way when you can estimate a number of limit cycles more precisely?
Why in a focus you can estimate the number of limit cycles?
Because you have the
Okay,
pointer MAT.
because you have the Lyapunov constants.
Yes.
And using the Lyapunov constant, you can control some number of limit cycles which bifurcate. In the node, for the moment,
The argument
There
is
are
the Pointer-Riemann theorem.
there are no similar thing as Lyapunov constants. So this is that I don't know tools for answer this
Yes.
question because
For any n, you can construct easily an example with n limit cycles.
Yes,
Not n, m, for any m, if n is not in the polynomial case. You can construct an example under this hypothesis with any number of limit cycles. So there is no upper bound in general. It's easy, just in polar coordinates you put all work. So there is no upper bound. In your theorem, changing the stability, you can have any number of limit cycles.
que era viernes.
No, any number. For any n, I can give you one example.
Bifurcating from the equilibrium.
Yes.
But for instance, in quadratic systems, at most 3, because it's proved by Bach.
Yeah, but
So,
I mean,
Increasing the degree, of course.
there is no degree. This theorem is a theorem that you have a focus that changes a point that changes stability, and you can have any number. Of course, if you fix the degree, no. But you don't fix the, you don't have degree at the beginning.
If you don't fix the degree, I agree.
Of course, if you fix the degree, I don't know. But if you don't fix the degree,
Yes. If you don't fix the degree, I agree with you.
Other questions, comments? In the Hopf situation, the Hopf bifurcation, the limit cycle that appears locally is hyperbolic. Can you say something about the hyperbolicity of this limit cycle?
No,
because of the technique.
you need the Poincare map to define the hyperbolicity. We don't have here a Poincare map.
Yes, for me equal to 0, we don't have. But when the limit cycle appears, there is a Poincare map defined around the limit cycle. But we can't say anything about the...
When there is a limit cycle, you have, in the neighborhood, of course, you have, of the limit cycle, you have a Poincare map. But this limit cycle, the Poincare map does not arrive to the region. So, for the moment, I don't know tools for controlling the number of limit cycles bifurcating from a node and the number and the kind of stability.
But the kind of stability, we can say something, can't we?
The one which is more close to the region, you know, and the others depend.
But I think that if we know the stability, we can do a kind of perturbation. I don't know, Paulo have done something like that. We can do a kind of perturbation using rotated vector field and ensure the existence of at least a hyperbolic one. I think it's another
In general,
reasonable.
in general, you cannot apply rotated vector fields. You only can apply.
No, it's a perturbation. Yes. Claudine?
In this context, I was just going to ask you, do you have an example of an analytic one-parameter family where the limit cycle is not hyperbolic, where you have a stable one which is not hyperbolic?
I don't have this example.
I do not want to claim that it will always be hyperbolic, but I would like to see an example, and because often when you have a 2-parameter family, 3-parameter family, you have somewhere, let's say, limit cycles that are not hyperbolic. But I would like to see an analytic one parameter where you immediately create a non-hyperbolic, because often when you create a lot of limit cycles, they are all hyperbolic.
Yes.
Stupid question, maybe.
But perhaps not easy answer.
Okay. Any other comment, question? Paul?
About the question of Professor Gazou, I think that if you could go back one slide, please.
What do you want?
Yes, this one. If you take this example of this n of n plus 2, and we apply the same reasoning on this example, like multiply it by x squared times y squared, and then put a new parameter, a lambda, it will satisfy the question of Professor Gazou. Of course, the degree will increase in 2, but it is at least an example.
You have answered the question of Professor Gazou.
And about what Professor Douglas said about the rotated vector fields, in case of a fold, if I am not mistaken, in case of a weak focus, independently of the degree of the weak focus, if you rotate it, it will bifurcate exactly one limit cycle. Duff had proved this. I do not remember if this limit cycle is hyperbolic in the case of focus, but some way something could happen in the case of node. Something like that could happen in case of node. I do not know, but there is an interesting idea.
For instance, in quadratic systems, using bounding results, you can bifurcate one limit cycle which is semi-stable. Consequently, it's not hyperbolic.
Okay. Any other comments? No? So let's thank the speaker again.
This
We have 10 minutes until the next objective of maps. So join me in a round of applause for the speaker.
So thank you very much for this, and it's my pleasure to be here to talk in this event that I like a lot, especially when it is the anniversary of Professor Marco Teixeira. So here is Professor Marco Teixeira was in the committee of my PhD defense. Here is Teixeira, Clodoaldo, Toscano, my advisor Rudival and Jorge Olim. And this was in 2010, 11? No, 10. Okay. So, and I met Professor Marco Teixeira in this day, in the day of my defense. And then we was enrolled in a postdoc with him, and we worked together in this subject. So, I begin with a map of class C1, such that the Jacobian, and in this talk, J of F is going to be the Jacobian, which is the determinant of the Jacobian matrix. And I will ask that this is different from 0 throughout Rn. Of course, this is a local diffeomorphism, but you know it is not necessarily global. And a very simple example, but interesting one, because the Jacobian is 1, constant 1, but of course, because of this cosinus and sinus, it is not injected. And it never attained the origin, so it's not surjective as well. So there is this global invertibility problem to search for conditions to put together to the Jacobian determinant different from 0 in order to get global invertibility. That we could say to globalize the inverse function theorem. There is a very appealing thing in the polynomial case. Why? Because is enough to assume together with the Jacobian different from 0 that F is a polynomial map, and only in 9. This is a very natural question. If it is a local, the diffeomorphism is global. So only in 1994 that a counterexample for this appeared. So it is interesting that. But more interesting is that if you assume polynomial, and here the domain can be R or C, so think about R to N, but a polynomial map in Cn, with Jacobian constant. And this is, of course, here you are asking that is global invertible and the inverse is polynomial. And this is open since 1939. This is a conjecture posed by Keller. And Ismail, in 1998, he has a list of 18 problems to be solved in this century. In the next century, it was 1998, so it is this century. And Jacobian conjecture is the problem 16. And the problem 16 of Hilbert is the 13th in the list of Ismail. So it is an important problem. Just a comment. In the polynomial case, it is enough to deal with the injectivity, because the injectivity will provide the surjectivity in the polynomial case. And in the polynomial case, in C, the injectivity provides the surjectivity, and the inverse is also polynomial. It is not known in the case of R. It is not known that the inverse is polynomial. I will talk about two ways of seeing this problem. One is by Yellow-Nex conjecture, and another one is using surjectivity of vector fields. And we will provide a theorem on the global invertibility problem by these two ideas. So Yellow-Nex conjecture. But I begin with the Hadamard global invertible theorem. So consider X and Y connected spaces, topological spaces, and Y simply connected. And consider a local homeomorphism. In my problem, I always have a local homeomorphism. It is a local diffeomorphism, but in particular, it is a local homeomorphism. And this local homeomorphism is a global homeomorphism if and only if F is a proper map, that the preimage of compact set is compact. Why? Because if F is proper, why is this true? Because if F is proper, then it is a covering map because it is a local homeomorphism. Since X is path connected, there is a map from the pi1 of y0 in y0 to the fiber of y0. But since Y is path connected, this is trivial. So the fibers are singletons. Okay? And so F is bijective and then a homeomorphism. So this is the proof of the Hadamard global theorem. Of course, the converse is trivial because if you have a homeomorphism, the preimage of a compact is going to be the image of the inverse function, which is compact. Okay. Now, consider a in the case of R or C. Consider a continuous map, and I will define that this map is proper, so it doesn't need to be the same dimension. I will say that this map is proper at some y, km, here is km, in the target. Okay? If there exists a neighborhood V of y such that the preimage of the closure of this map is compact. Okay? And I will consider the set of non-properness, the non-properness set of F. So we will consider all the, this is, here is correct, here is M. I will consider all the points at the image, at the target, such that F is not proper at this point. It is not difficult to see that this set is empty if and only if the map itself is proper. You cover the compact set and you see. So the idea is that the size of this set tells us somehow how far we are from a proper map. And it is interesting that this set has some algebraic and semi-algebraic properties. For instance, if F is semi-algebraic, this is semi-algebraic also. This set is semi-algebraic. You can calculate it. And in the special case of the Jacobian conjecture, when the Jacobian is 1 and F is polynomial, more than being algebraic, it is also a hypersurface. In any case, so this is works by Yellow-Nex. In any case, we can consider the codimension of this set, because if it is a hypersurface, the codimension is 1, of course, but if it is semi-algebraic, we can stratify the set and consider the dimension, codimension of the set. So we can say that this set is small or big by looking to this dimension, codimension. Okay? So, in case we return to the case of C infinity and semi-algebraic in order to consider the codimension, with the Jacobian different from zero. So I have a local homeomorphism, okay, a local diffeomorphism, if you right. And if the codimension of this set is big enough, so if the codimension is greater than or equal to 3, this means that this set has dimension, it is smaller, dimension less than or equal to 3. It is enough for, then F is injective. Okay? And it is very simple to see this. Of course, it is not simple to see that Rn minus SF is simply connected, but the idea is that the size of the set is small enough in order that the complement is simply connected, and the complement of the preimage is connected. So by using covariant reasons, okay, by using covariant reasons, the restriction of the map to this set is proper than a homeomorphism, as we did before. And you can prove that SF does not intersect the image, and then you get an injective map, so that F is injective. But recall Pinchuk example, a polynomial map from R2 to R2 with Jacobian different from 0, not injected. In the Pinchuk example, SF has codimension 1. And of course, that we can make a Cartesian product with the identity, and we can construct a non-injective local homeomorphism polynomial map, okay, such that the codimension of SF is 1. Here is the set SF for Pinchuk map. It is a curve. You can parameterize this curve. In this work, this is done. Here's the preimage. You see, it is not connected. The complement of the preimage is not connected. And of course, the complement of this curve is not simply connected. You cannot apply the covering reasons. But so codimension 3, injectivity. Codimension 1, not injectivity. So it remains to study what happens with codimension 2. This is the Yalomek's conjecture. If F is semi-infinity and semi-algebraic, with Jacobian different from 0 in Rn, and the codimension is 2 or bigger than, higher than or equal to 2, the conjecture says that F is injective. It is true in dimension 2. Yalomek proved this in his paper. But what is the most interesting fact about this conjecture is that if it is true in dimension 2n, in real dimension 2n, then the complex Jacobian conjecture is true in dimension n. Why? Because if you consider a map from a Cn to Cn, we have seen that SF is a hypersurface. So it has codimension 1, a complex codimension 1. So if we think about this map in R2n, the real codimension is 2. And if this is true in dimension 2n, so it's the Jacobian in dimension n. This is Yalomek, okay? And here is a result. And so people started working with this conjecture. Here is one result by Fernandes Maqueira and Donato Santos. It is a map from semi-infinity and semi-algebraic, the same assumption, the Jacobian, but now with the assumption of codimension greater than or equal to 2, the dimension of the non-properness set. They put an assumption more. They pick 2 indices and consider this intersection. So if you are in R3, for instance, this is the level sets of each coordinate. It is the fiber of each coordinate. So this intersection is just a hypersurface of dimension 2. It has dimension 2. It is a surface, of dimension 2, because I am picking the fibers, but two of the points. Then is a global diffeomorphism. This was proved by them. Now, I told you that we will talk about vector fields also. So, consider a map here from Rn to Rn or Cn to Cn. In the case Rn it is C infinity, and in case complex is holomorphic. And define this operator. So this operator picks functions, C infinity functions from Rn to R, and transforms in a function from C infinity function. How? Or it takes a holomorphic function and it is a delomorphic function. What it does? It considers the function, and it is the Jacobian of f1, fy minus 1, and in the place of fy you put g. So it is, you can see this operator here. It is the Jacobian determinant that in the line I you put the gradient. Okay, so it is an operator, it's a vector field. Think about in dimension 2. In dimension 2, for instance, you have f1, f2, and here partial x1, partial x2. This is the Hamiltonian. So in dimension 2, it is just a multiple of the Hamiltonian system, Hamiltonian vector field. Okay. In particular, this vector field, in the case of the Hamiltonian, you know that the orbits of the Hamiltonian of Fj, the Hamiltonian of Fj, are the fibers of Fj, the connected components of the fibers. Here, this property it keeps. The orbits of these vector fields are the connected components of all the intersections F1, F2, minus 1, the fibers of each of them, but the Y1. Okay? So all the intersections F1 minus 1 of C1, intersection F2 minus 1 of C2, all of them are the orbits of this vector field. So there is this theorem that in the Cn case and polynomial with Jacobian equal to 1, f is injective and so surjective because it is a polynomial, if and only if this vector field is surjective, is onto. This means that I can always solve the equation. I put this equation here. I wrote this equation, delta IF G equal some F. I can solve this. This means that it is surjective. It attains all the functions in the target. Okay? For n minus 1 indices, then it implies the injectivity. And so the surjectivity. This, in 3 papers of Stein, and then Krasinski and Spodzieja later, they proved this, first for R2, then for Rn, and so. In Rn, an analogous statement in the case of C infinity would be that, as I said, the vector field is surjective for n minus 1 indices, then f is injective. This would be the analogous in Rn. Okay, if I can solve the equation for any C infinity map, then f would be injective. This is true in R2. You can see this in this paper that I mentioned with Professor Marco Teixeira. In this paper, we also characterize the surjectivity of this vector field by using geometry, by using some geometric. I will not talk about this a lot today, but you can see, for instance, that this is true in R2, but in higher dimension it is false. There is a counterexample with Professor Ridgwell. So what is the main theorem? It is to put the surjectivity of the vector fields in Rn together with the assumption of Yelonic. Only Yelonic we do not know if it is true. And without the vector fields, it is not only the vector field to be surjective, it is not true. So we add the two conditions. Adding these two conditions, this means that F is bijective if we put the two conditions. And this was done with Luis Renato Gonçalves Dias and Jean Renato Santos. But recall that in the case of CN, SF is a hypersurface. So if it is a hypersurface, in thinking about it has codimension 1, so in the real case it has codimension 2. So its real codimension is 2. Is higher than equal to 2. And also that without the assumption on SF, this is false in Rn. So this theorem is the natural real counterpart of the preceding result. Because in the preceding result, the Stein and so result, that the codimension of SF is greater than or equal to 2 is natural. This is always true. So this is the natural theorem. And we can put this conjecture. Assume that F is polynomial, the codimension is greater than or equal to 2, the codimension of the non-proper set, and you can add that n minus 1 indices of this vector field is surjective. You put that, you assume the Yellow-Nex conjecture, and this is going to be the consequence, and so this is 2R theorem, this implies the Yellow-Nex conjecture, and so the Jacobian conjecture in dimension n. Now, how to prove this theorem? Recall that, let me just return here. This is the theorem by Fernandes, Maqueda, and Renato Santos. They consider all the intersections without two of them. And they say that if these intersections are diffeomorphic to R2, then F is global invertible. So we will prove this. So if I assume that the vector field, one of the vector fields, delta I, is surjective, then for any J that I consider but Y, then for any non-empty connected of set, any non-empty connected component of this intersection is diffeomorphic to R2. So this is that we are going to prove. Because if now I consider n minus 1 indices of, if I varies n minus 1 indices in from 1 to n, I will have that all the intersections are going to be union of planes. The connected components are going to be diffeomorphic to R2. And I assess the main result will follow from their theorem. Now, in order to do that, I would like to recall a relationship between analytic and dynamical properties of a vector field. So consider a vector field. It is surjective if and only if none of his orbits is contained in a compact set. So it cannot have singular points, nor periodic orbits, and so. But more than that, for any compact, there exists another compact K prime, such that every interval of orbit of X with n points in K is contained in K prime. So it is like this. For any compact that you consider in Rn, this is K. There is another compact that I don't know the size of this another compact, such that each interval of orbits of my vector field with n points in my first compact is inside each interval orbit is inside the K prime. So for instance, you cannot have you cannot have those half-rib components. You know, those half-rib components in the IR2 you cannot have, because this is going to be a compact, and for any compact that I will consider, I can always have an orbit escaping this compact set. So this is the result of Juister-Ma and Hormander. And recall that the orbits, I told you that the orbits of delta I are the connected components of this intersection. And since it is the intersection of these connected components, for instance, if it is R2, it is the Hamiltonian. It is just the connected components of one of them, the connected components of Fy. But in particular, if I remove one of the intersection and consider L being a connected component of this intersection, my vector field is invariant in this surface. I mean, so I have a vector field which is invariant in L. And the orbits in this restriction, because the orbits are all the intersection, I remove it one and consider a connected component of this intersection. But in this L, what are the orbits? The orbits of the vector fields are going to be the fibers of the restriction of Fj, exactly the one that I removed, because it is the orbits is the intersection of J minus omnus of Cj that I have to put here in order to get the orbits. But since I cannot have this, because my vector field is surjective, I cannot have this, so I am in a surface here. This is my surface. I cannot have something like that in this surface, because otherwise it is not it will not be surjective. Then I cannot all the level sets of this function Fj are connected, because if there is two of them that are not connected, I can produce something like this. I can produce a half-rib component. So we can prove that the fibers of Fj are connected. More than that, the fibers are homeomorphic to interval to R, because the fibers, as I told you by the result here, no orbit of X can be contained in a compact set, so it is homeomorphic to R. So we have a trivial fibration. All the orbits are all the fibers are connected, and they are so it is a trivial fibration with fiber being R, and it is not difficult to see that the L must be homeomorphic to R2 as we want. And so this proves the result. Here is a picture with Marco Teixeira from the last time he was in São Carlos, at the beginning of this year, with two students. And happy birthday, Professor Marco Teixeira.
Thank you very much, Francisco. Questions, comments? Question here, Lucas.
Thank you, Francisco. My question is about the injectivity that you have for polynomial maps on Rn. The result about saying that the coordination of this non-proper Tillman set is self-coordination at least 3. So I understand that this is for any n, any value of n.
N, yes.
So
yes.
Where this lower bound, this number 3, come from?
No, it is because the number 3 is enough, exactly because of this. It is exactly because of this. So it's because when you, the proof is here. Here. When you consider the complement of this set, the codimension greater than or equal to 3 is enough in order to this codimension to be simply connected. Since this codimension is greater than or equal to 3, this means that the set is small enough in order that its complement to be simply connected. And since it is simply connected, and more than that, the complement of the preimage is connected, but then we have a proper map. We have a covering map. That's the point. So my restriction is going to be proper, but since the spaces, this is simply connected, and this one is connected, this is a covering. So this lower bound, it is in order to be small enough or big enough, the complement to be big enough in order to be simply connected, and in order, so we can reason by covering. We can use covering reasons.
Okay, so the number 3 is because of this.
Yes, number 3 is because the size is small enough.
Okay.
But and more, dimension 1 is not codimension 1 is not enough because we have counterexamples. So the conjecture is codimension 2.
Right, okay.
So we need to know what happens in codimension 2.
Thank you.
Thank you. Any other question, comments? No? So let's thank the speaker again. Thank you for all the speakers of this morning section. We shall have lunch now, and we'll be returned at 2 o'clock.